All right, team, welcome. It is so great to have our new crew of entry-level field surveyors here today. For this engineering briefing, we're zeroing in on something you're going to use every single day on the job. We are talking about mastering the global coordinate system. As field surveyors, your entire profession is literally built on knowing exactly where things are, right down to the millimeter. So let's dive into this explainer and make sure we all have an absolutely rock-solid foundation. I want you to picture a scenario. You're out on site, and someone asks you, can you tell me the exact location of a specific building? Let's say a specific structure somewhere in Pakistan. But here's the catch. They don't want the city name, and they don't want the country name. They need the exact, precise point on the dirt. So how do you describe one unique location out of billions of possible places on Earth? Well, the answer lies in just two numbers, and those numbers form the invisible lines of our global coordinate system. So here's our game plan for today. 1. The global address. 2. Latitude, the rows. 3. Longitude, the columns. 4. The intersection. 5. GPS and GIS applications. And finally, number 6, field rules and mnemonics.
Okay, starting with part 1, the global address, basically house numbers for the Earth.
Think about working in a massive, sprawling, modern city. Without house numbers, finding one particular building would be completely impossible, right? Well, the Earth needs an address system in the exact same way. To visualize this, I want you to think of something we all use all the time, a giant spreadsheet. Just picture latitude as your horizontal rows and longitude as your vertical columns. This is your universal addressing system. Let's look at how that actually plays out in reality. Every single location on Earth can be identified using one unique pair of these coordinates. Take Islamabad, for example. Its exact address is 33.6844 degrees north and 73.0479 degrees east. Just like a highly specific house number on a very specific street, these two values lock in one exact, undeniable location on the surface of the planet. Moving on to part 2, latitude, the horizontal rows, and understanding parallels. By definition, latitude measures exactly how far a location is north or south of the equator. You know, that imaginary circle dividing the Earth perfectly into the northern and southern hemispheres. Now, notice how these latitude lines run horizontally around the Earth? We call these parallels for a very simple geometric reason. They never meet, they're just perfectly parallel rings stacked one on top of the other. The really crucial point here is the numbering system. Since the equator is our starting line, its latitude is exactly 0 degrees. From there, the values range all the way up to a hard cap of 90. That's 90 degrees north when you hit the exact North Pole, and 90 degrees south when you reach the South Pole. There is absolutely no latitude greater than 90. Let's ground this with some actual numbers. Look at Lahore at 31.5 degrees north versus Karachi at 24.9 degrees north. Because Lahore has a higher number, you as a surveyor instantly know it's further away from the equator than Karachi is. London sits way further up at 51.5 degrees north, while Sydney drops down into the other hemisphere at 33.9 degrees south. The rule of thumb is simple. The higher the latitude number, the farther you're moving away from the equator. All right, part 3, longitude, the vertical columns, and understanding meridians. So, while latitude does north and south, longitude measures how far east or west a location is. And this brilliantly illustrates the key difference between our two sets of lines. Longitude lines run vertically from the North Pole all the way down to the South Pole. Unlike our parallel latitude lines, all longitude lines physically converge and meet up with poles. Think of them kind of like the segments of an orange. Just like latitude needed a starting point with the equator, longitude kicks off at the prime meridian. The prime meridian passes right through Greenwich, England, and its longitude is 0 degrees. From there, locations to the east have east longitude, and locations to the west have west longitude. But instead of stopping at 90, longitude values range from 0 degrees all the way up to 180 degrees east and 180 degrees west, meeting right on the exact opposite side of the globe. Let's look at some longitude examples to see this in action. Islamabad is 73 degrees east of the prime meridian. New York is 74 degrees west, Tokyo is way over at 140 degrees east, and Los Angeles is at 118 degrees west. This single number tells you exactly how far around the globe you've traveled from that starting line in Greenwich. Which brings us to part 4, intersection, finding the exact point where rows meet columns. Listen, this is the single most important concept for your day-to-day work. As field surveyors, you know that half a coordinate is entirely useless to us. Latitude alone cannot locate a place. It just gives you a massive ring wrapping around the Earth. Longitude alone cannot locate a place. It just gives you a massive line stretching from pole to pole. But when they intersect, they define one exact, precise point. Just like finding that single, unique cell in a spreadsheet where row 33 meets column 73. That exact intersection is the entire foundation of how our location technology works. Let's look at Part 5, GPS and GIS applications, essentially the tools of our trade. Whether you're holding a $50,000 field rover or just opening Google Maps on your phone, the underlying mechanics are exactly the same. First, your device communicates with several GPS satellites orbiting the Earth. Second, each of those satellites calculates its exact distance to your device. And finally, by combining the signals from multiple satellites, your device triangulates your precise latitude and longitude. Within seconds, your exact grid location is locked in. This is the invisible math powering literally every drone survey and infrastructure project we do. And hey, it's not just us out in the field relying on this. Notice across the different disciplines here how foundational geographic information systems, or GIS, truly are. In GIS, every single point feature stores these coordinates. We engineers use them for critical infrastructure planning. Hydrologists use them to map out massive rivers and watersheds. Climate scientists rely on them to analyze data from global weather stations. Without latitude and longitude, digital maps, and frankly modern engineering as a whole, simply would not work. And finally, Part 6, Field Rules and Mnemonics, or How to Never Confuse the Lines. Look, as beginners, it is incredibly easy to confuse these lines, especially when you're 12 hours into a shift on a hot day, and mixing them up can result in some extremely costly engineering errors. So I want you to memorize this trick right now. It's simple, but it works every single time. Latitude is flat, longitude is long. Say it to yourself. Latitude lines are flat horizontals, like the rungs of a ladder. Longitude lines are long, extending vertically all the way from pole to pole. And here is the second half of that cheat sheet to contrast what they actually do. Latitude tells you how far north or south you are. Longitude tells you how far east or west you are. Burn this into your brain right now. If you remember that latitude is flat but measures north and south, and longitude is long but measures east and west, you will never end up digging a trench in the wrong district. So you've now got a solid handle on the global coordinate system, the invisible rows and columns that wrap our planet. But here is the massive curveball that keeps surveyors awake at night, and it's the question I want to leave you with today. The Earth is a 3D sphere, right? But the blueprints and the maps we use out in the field are completely flat 2D paper. So now that you know the grid, how on earth do we project a round planet onto a flat map without hopelessly distorting all of our measurements? Well, that requires geographic coordinate systems and map projections, which is exactly what we'll be tackling in our next explainer. Thanks for joining me today, team, and I will see you out in the field.